And I would like to start by inviting Diego, Dave, and Mao, who will be presenting on traffic engineering essentials for automation orientation. All of them are coming from Nokia. They work at Nokia, mostly supporting network automation products. They are coming to us today from California, Ottawa, and Texas, respectively. This is Diego and Dave's first time presenting at NANOG, right? All right, it's a pleasure to have you. Welcome to San Diego. And this is Mao's sixth time presenting at NANOG. Mao's first talk at NANOG was back in 2022, and the topic was the power of Kubernetes CRDs at NANOG 85. Welcome back, Mao. And it is a pleasure to have you all come on stage and present to us today. Please come on.
Okay, hello everyone. Well, as Les was saying, my name is Diego Achaval. I've been working for Nokia for the last, or with Nokia for the last 8 years. Based in San Francisco these days, working out of the Bay Area, mostly in all technologies related to MPLS, MPLS, path computation, segment routing, and everything. I don't know, Dave, if you want to.
Sure. Dave Watkinson. I've been at Nokia all the way back to Newbridge times. If people remember that company, that was almost 30 years ago that I joined. Been working on mostly in the R&D side of things. Just moved recently into product management on the NSP side of things. So mostly focused on the path computation engine side of things. So
perfect. Thanks, Dave. So what we wanted to talk about in this presentation is basically traffic engineering. And this presentation, before we continue, is just part of a session of a series of 2 presentations that we are going to have at NANOG this year. So this one is an introduction to traffic engineering, or essentials of traffic engineering. So we will be discussing several technologies associated to traffic engineering, and then Dave and Mao will be talking about path computation, centralized path computation, and closed loop automation, and then Mao will be talking about how to automate traffic steering using traffic engineering and open APIs, in order to be able to program a network specifically to steer traffic across the network, right? So this is the agenda, as I was saying: traffic engineering overview, or PCE or PCEP overview. We will be talking about BGP-LS, as I was saying before, IETF APIs for traffic engineering, and then we have telemetry and PCE combined for closed loop automation. Okay, so well, introduction. As I was saying before, what are we trying to do? What people is trying to do with traffic engineering is basically optimizing performance or optimizing resources utilization in a network, yeah, and ensure that we have efficient data flow and optimize or improve overall network resource utilization. That means using certain links, avoid using certain links, avoid congestion across the network by optimizing resource utilization, okay? And for that, so we have traffic engineering, which is basically resource optimization, performance maximization, that is running a hotter network by trying to use as much bandwidth per link as possible, and also to enable scalability and flexibility, and to provide also local end-to-end protection, as we have been always doing with traffic engineering. So on the predictability side, so why traffic engineering is crucial in networks? It might be an MPLS network, and these days it might also be an IPv6 network or an SRv6 network. Okay, so I just forgot to add that there. So one of the crucial or several of the crucial points is predictability. So this is the ability to know how your traffic is being steered onto the network, and to know and understand traffic patterns across the network. Then customization. So for example, we have always seen operators trying to steer traffic onto specific specific paths in order to satisfy specific constraints that certain traffic may have, right? And then resiliency. Of course, with traffic engineering, we have always had the possibility to provide end-to-end protection and to provide local protection using fast reroute. These are very, very classic or crucial points for traffic engineering. And now, what are the key components of traffic engineering? So, first of all, we have this concept of traffic trunks, which is basically a certain type of traffic that needs to be treated in a specific way. So we can say, like, for example, a class-based traffic may be considered as a traffic trunk because all the traffic that goes into a specific path is going to be treated in the same way across the network. Then we have, of course, constraint-based routing, which is also key in traffic engineering networks. This is just to optimize or build traffic engineering paths based on specific constraints imposed by these traffic demands, okay? We can use, nowadays, we can optimize based on end-to-end IGP cost, or we can optimize based on traffic engineering metric. These days, in using end-to-end delay, which has become very important for multiple operators and for multiple customers. So, and also, of course, there are another series of constraints that we can satisfy using traffic engineering. So, of course, admission control is being always a key differentiator or a key point for traffic engineering too, in order to be able to place LSPs or paths onto specific resources in order to satisfy, for example, bandwidth requirements per LSP, right? And then policy enforcement. Okay, this is a way to basically keep traffic onto those paths and verify that traffic doesn't behave badly or doesn't go above what is being reserved for them. Okay, so that would be kind of policy enforcement. Now, we have several technologies for traffic engineering. We have standards-based, IETF-based technologies, and we also have non-IETF or proprietary technologies. So on the IETF side, of course, we have RSVP-TE, which has been there forever, right? It's been there for more than 20 years now, okay? These days, we also have segment routing-based traffic engineering, right? So for segment routing, we can use segment routing with multiple data planes. So we can keep using MPLS, or we can use an IPv6-based transport, which is also known as segment routing v6 or SRv6. But we also have the possibility of using traffic engineering with flexible algorithms, right? So flexible algorithms is a way for our classic IGP algorithms that we use in the network to build a specific or constrained topologies that are optimized on a specific objective. As I was saying before, we can use IGP cost, we can use TE metric, or we can use end-to-end delay, along with other optimization or other constraints to build that specific topology. And of course, we have centralized. So we have traffic engineering mixed with centralized path computation, this is something that Dave and Mao are going to be covering later today and tomorrow in the second session of this tutorial, right? So a bit more details about, sorry, let me just go back. I forgot to mention the non-IETF proprietary technologies. So Dave here is going to be covering closed loop automation using PCEP and telemetry, okay? And then we will also be covering, along with both Dave and Mao, we will be covering automation-driven traffic steering during the second session of this tutorial, okay? I don't know if you will want to add something. Yeah, perfect. Excellent. So, traffic engineering. So, during the last 20 years, we've been using, we have been using the resource reservation protocol in order to be able to signal or build or instantiate paths or LSPs across the network, right? So this is very well known. As I was saying before, basically what we do with the traffic engineering path is first we compute a shortest path based on a specific optimization objective, okay? Which in this case, the well-known options there are, as I was saying before, IGP cost and TE metric, okay? But these days we also have the possibility of using end-to-end delay, which is, again, as I was saying before, a very interesting use case for most network operators. And we can also include these days, or it has always been there, but there are implementations that support bounds or not, right? So we can have an upper bound in order to further constraint, to add an additional constraint to the path computation algorithms in order to build and instantiate these paths, right? So we also have the classic constraints like bandwidth, for example, whether we may require a bandwidth demand for any given LSP. We also have the constraints like path protection, and in this case, well, sorry, I would say local protection or end-to-end protection. So RSVP has always given us the possibility of signaling LSPs, primary, secondary LSPs, and also have these LSPs being protected across the path using local protection or fast reroute. So we have a couple of flavors to do that, but also we have the possibility to have end-to-end protection by having primary and secondary LSPs and switch traffic from primary to secondary upon the failure of the primary path, right? There are several options in there too. So, and we also have constraints like admin groups, very famous, right? So those have been always being used by network operators for different reasons, right? So one of the reasons is to use link coloring associated to disjoint constraints in order to have associated paths and have them using different network resources in the network to avoid, single points of failure, okay? And we can also use link colors. For example, we have seen operators trying to keep traffic within the boundaries or the borders of a country, okay? So this is a way also to color links in a specific way in order to keep those LSPs using those specific links, okay? So we also have, so as you know, of course, with RSVP, we support call admission control using bandwidth requests or bandwidth reservations, okay? So we have had for a while also now this feature or this extension to RSVP-TE called, or extension to MPLS traffic engineering called auto bandwidth. So this is the possibility of an LSP to automatically grow its bandwidth reservation based on real or near real-time bandwidth measurements or bandwidth utilization. Okay, so we have the possibility to, with auto bandwidth, an LSP, and any given LSP is going to be measuring bandwidth utilization on a period of time, and based on those measurements, a new reservation is going to be fired by that specific LSP, or it can be just it can be fired to update the bandwidth reservation to a larger quantity, or it can be fired for a bandwidth reservation to be reduced for that specific LSP. So we have seen implementations out there for a while related to this technology, and I have a specific slide for so I have a specific slide for this technology. This is a draft, as you can see up there, that it never became a working group document at the IETF, but we have seen several implementations out there, and we have seen network operators using this technology. And what this technology allows is first of all, it's a combination of auto bandwidth and also the dynamic instantiation or deletion of LSPs in order to accommodate dynamic bandwidth demands. Okay, so in RSVP-TE classically, we will have a single LSP following a single path, so all the traffic may always be carried using the same nodes and links. Okay, so now with this technology here, what several operators are doing is just basically measure bandwidth over a period of time, and then when the bandwidth utilization on any given LSP reaches a specific point, these implementations, what they will do is just dynamically instantiate a new LSP and dynamically do ECMP across multiple LSPs, okay? So this solves several problems. The first problem that we solve with this is, the bin packing problem. So with MPLS traffic engineering and RSVP, there has been always an issue where LSPs may not be instantiated or may not be allowed to be created in the network because we may not have enough bandwidth resources at any given time in the network, right? So, in fact, we may have. The problem is that LSPs are distributed in a way where we may get to a state where we do not have enough bandwidth resources, but we actually do have bandwidth resources. So with this, what we do is create disjoint LSPs, right? And then we load balance traffic on top of those LSPs. And we can create as many LSPs as required. So I've seen implementations out there allowing to create hundreds of LSPs associated to a primary. First, you will have a primary LSP, and then sub-LSPs that may or may not take a different path, but the idea is to have a more balanced network bandwidth utilization using multiple LSPs across multiple available paths, and to do, let's say, some sort of equal cost multipath, right? So but at some point in time, you may have more bandwidth on a single LSP or less bandwidth in other LSP. So there might still be some issues, even though in that area with these extensions to RSVP, right? So that's of course, with these extensions, we can still take advantage of dynamic LSP bandwidth resizing with auto bandwidth, because you may have a number of LSPs being created, but then you have a limit, right? So you will not be creating more LSPs. So if the bandwidth demand increases, so we have RSVP using auto bandwidth in order to update the bandwidth reservations for those LSPs. We also, so as I was saying before, efficient load balancing, of course. Then we can take advantage. So any sub-LSP or any member LSP of this group of LSPs can still take advantage of, the well-known mechanisms like local protection and restoration. And one of the main advantages of a solution like this is the automation of the creation and deletion of those LSPs, right? So there is no human intervention required to create those LSPs. So now going to segment routing really quick here. I don't know how familiar people are with segment routing. I will assume that you all are familiar with that. So segment routing basically allows for an ingress node to compute a path to any given endpoint in the network and to encode forwarding instructions on top of that packet. Okay, so forwarding instructions in an MPLS. So it's basically forwarding instructions are basically a list of segments that are encoded in a packet or on a packet that tells the packet how it needs to be routed across the network. And everything is on that specific packet header. Okay, so with segment routing, for example, in segment routing and traffic engineering, there is no need to maintain state and waypoints across the network between a pair of devices establishing an LSP. Okay, so and then once those instructions are encoded on that packet, we have intermediate nodes executing those instructions, okay? So, or forwarding those packets according to the instructions that have been encoded on that packet. So as I was saying, so segment routing with an MPLS data plane can be used, sorry, I mentioned before that segment routing can be used with both MPLS and IPv6 data plane. But also, segment routing with MPLS data plane can be used either with an IPv4 control plane or an IPv6 control plane. So you have options in there. So we have seen operators trying to migrate to IPv6, but they want to keep an MPLS forwarding plane and still be able to use all of these technologies or all of these advantages associated to segment routing, okay? But we have also seen operators trying to migrate to a full IPv6 data plane to be sides of an IPv6 or next to an IPv6 control plane. And for that, you can use segment routing v6 or segment routing with an IPv6 control plane. So let me just go back. So with MPLS, with an MPLS data plane, all of these forwarding instructions are encoded in label or as labels with an MPLS data plane and segment routing. In the case of segment routing v6, things are more complex. And in this case, depending on whether you are using compression with SRv6 or not, the forwarding instructions can be encoded for base SRv6. We encode the active segment or the active instruction, we encode that in the IPv6 destination address. And if we have to do traffic engineering, the rest of the seeds are encoded in the SRH, which the SRH is the segment routing header, which is a new header for the IPv6. It's a new header for the IPv6 header, okay? It's a new routing header, sorry. So Now, if we use seed compression along with SRv6, the segment list can be encoded both in the destination address and also in the SRH as carrier seeds, right, or container seeds. So we have a container seed that can encode up to 5 or 6 compressed seeds, okay? So we can encode that in the destination address and have the packet following a specific route, or we can encode additional compressed seeds or uncompressed seeds, whatever your path is using, in the SRH, in the segment list within the SRH, as you have said. So for SR-MPLS, we have, so I like to do a distinction between, so if you are familiar with SR-MPLS or SRv6, we have what is called SR policy. And SR policy is basically an entity that is formed by candidate paths, and candidate paths have multiple or may have multiple segment lists. Within an SR policy, we can have multiple candidate paths, and within a candidate path, we can have multiple segment lists. Now, with SRT-LSPs is similar to what we have with RSVP-TE based LSPs. The only difference is the difference we see in both is that how we do load balancing and how we can do primary, secondary, and protection for different candidate paths or different primary or secondary LSPs. So, as you can see here, so one of the main advantages of using segment routing TE or SRTE is the fact that waypoints do not need to hold a state associated to each LSP that traverses any given waypoint in the network. Okay, so this is a big advantage over RSVP-TE LSP. So, well, it's an advantage for some. It's not an advantage for others, right? So we have seen people that doesn't want to go away of segment routing, or sorry, RSVP-TE. They want to keep their network using RSVP-TE, so that's fine. So this is one of the advantages that we have one over the other. So we support. So the industry supports on-demand instantiation of this, on-demand or intent-based instantiation of these sort of LSPs. So in SRTE or in SR policies, we use what is called adjacency seeds, node seeds, adjacency set seeds, or BGP-EPE, or even binding seeds in order to build the seed list that is going to be used to steer these packets across the network, okay? And now, an important thing related to an important, well, it's not a problem. It may become a problem with segment routing TE LSPs is the number of labels that any given device can push on top of a packet in the ingress of the network or at the egress of the network. So some different vendors, different hardware, they support different number of labels they can impose on a packet. So in this case, the base MPLS imposition, as I was saying, may become a challenge depending how deep is the network. There are solutions for that. So every network vendor that you may know may have a different way of solving this issue by compressing the label stack using different techniques. This is just not it's not standardized. It's something that every vendor do in a different way. Okay, one of the ways of doing this is by computing an end-to-end path and then replacing sections of an end-to-end SRT-LSP using binding seeds, and then the path gets expanded whenever the packet reaches a point in the network where a binding seed is being instantiated or has been instantiated. So that's a nice way, an elegant way of solving this. You can do this with distributed path computation. Some may support that, or you may take advantage of a centralized path computation elements in order to avoid these limitations or these problems, right? So then a differentiation here, SRT-LSP. So we are talking first about SRT-LSPs. So we can have explicit or dynamic paths with either distributed or dynamic or centralized path computation, which, well, with SRT-LSPs, you support multiple, or one may support multiple optimization objectives, as I was saying before. Again, the same as with RSVP-TE LSP, IGP cost, Telemetry, end-to-end delay. And traffic steering can be done in multiple ways, as is possible also with RSVP-TE LSP, right? So we can do that using colors. We can stay using, forwarding adjacencies, as we have been done forever as it has been done forever with RSVP-TE, or shortcuts, or with auto-bind, in that case, where specific services are just tied to a specific LSPs, a specific group of LSPs. So local protection, of course, there is a huge difference also in the way we can, or in the way we can have protection in RSVP, in SRT LSPs, sorry. One of those options is local protection using pre-computed repair paths using TI-LFA algorithms within each IGP. So most vendors also support that. Most network operators migrating to segment routing are listing this as an advantage of segment routing too. So, and we also have, so with RSVP, with SRT LSPs, as with RSVP-TE LSPs, we have the possibility of doing or supporting ECMP or weighted ECMP. The only difference in this case is that with SRT LSPs, you need to provision each LSP, right, in advance or dynamically, as I was saying before, right? So now SR policy. With SR policy, we also have the possibility to have explicit segment lists or dynamically computed segment list using distributed path computation or centralized path computation. That's the same. We have, again, support for multiple optimization objectives. We have support, this is very interesting too, native color-based steering. So one of the attributes of an SR policy is color, right? And with each SR policy, we have colors and endpoint, or a single color or multiple colors, in fact, and endpoint, okay? And then we can steer traffic on top of those seed lists using a specific color. So the traffic is tagged, or your routes are tagged with any given color. That means whatever you want to assign to them, you can steer that traffic onto SR policies. We can also do ECMP or weighted ECMP, in this case, in a more elegant way, because with segment routing policies, as I was saying before, we have candidate paths. We can have multiple candidate paths per SR policy, where only a single candidate path is going to be the active candidate path at any given time. And that candidate path may have, I don't know, 30, 40 segment lists, and each segment list may have a weight. If they all have the same weight, you will do ECMP you will do ECMP across those segment lists, but you may also assign a different weight to each segment list, so you can do weighted ECMP. So some segment lists may get more traffic than other segment lists based on any arbitrary attribute or decision that you may want to take, to steer that traffic on those segment lists. Okay, so now we have the same also. So the same we have for SR policy with MPLS. We have the same available also for SR policy with SRv6 data plane, right? So now, one of the differences here is the type of seeds that we use in these segment routing policies, right? So as you can see there in bullet point 3, so in SRv6, the seeds, they've got names. So for example, they may be called as N seeds or NX seeds, and they may have different flavors. And so that the combination of the type of seed and the flavor of that specific seed tells a node how to process that seed and what to do with the packets once those seeds have been processed. So as you may imagine, MSD, or the maximum segment depth supported in SR policies, can also become a challenge, because not all of implementations out there support a large number of seeds, either in the SRH or in the destination address field in the IPv6 header. Okay, so that's why we have had these days a lot of work being done around seed compression, right? So the ITF, several years ago, the ITF appointed a design group where they were analyzing all of the requirements for compression, and they have come up with a couple of solutions for compression that not all vendors are going to be supporting, the two solutions. There was a battle between one compression mechanism and another compression mechanism, so they got merged in a single working group document. So vendors may choose which option to use. One is called microseed, or colloquially known as microseed. The other is called G-seed, or generalized seed. So what we have seen out there is that most vendors are supporting microseed. Okay, so most of them, or basically all of them, and with one vendor only supporting generalize it, but that's trivial, right? So you know that you have the two options in there in order to solve that specific issue, okay? So again, we support, since this is an SR policy, but with a different data plane, we also support color-based steering onto those LSPs. So we also support local protection, again, the same way we do TILFA, or we compute protection or repair paths with an MPLS data plane. We do the same, using the same algorithms, maybe with some difference in implementations, but we also do the same with not with SR policies, but in general, for all the seats that can be protected or unprotected. Those who are protected are going to be having a repair path pre-computed by the IGP. And then all of the segments used in a segment list may take advantage of that or not. So, and of course, the same way as before, we can do ECMP or weighted ECMP per segment list. So, just quickly, referring to FlexAlgo, as I was saying before, FlexAlgo is the way to allow the IGP to build a specific topology using different optimization objectives, right? So in this case, the advantage of segment routing, the advantage of using SR algorithms or flexible algorithms versus segment routing TE is the fact that you will not need an operator, will not need to create LSPs. So the topology is going to be computed by the IGP, considering the optimization objectives or the constraints that we have defined, and you only need to steer the traffic on top of those topologies, right? So it can be done, the steering can be done in multiple ways. So you can steer based on color or on any attributes that you may have attached to your BGP IPv4 routes, IPv6, or even L2, L3 VPN routes, okay? And then, of course, FlexAlgo can use either an MPLS data plane or an SRv6 data plane. So we have different entities in for each data plane. So, for example, in MPLS, we are going to have per-algo seeds that we are going to be using to build these paths across the network. And in the case of SRv6, we have locators in SRv6, and each node gets a locator, and out of the locator, we assign multiple seeds for each node, right? So in this case, in the case of FlexAlgo, we have per-algo locators, okay? And of course, no per state is required in the network. So once this subtopology is computed by the IGP, is programmed in the data path across every device that participates in that specific topology or FlexAlgo. So you do not need to hold state per LSP in this case. So finally, I just wanted to touch really quick on centralized path computation and optimization before giving the mic to Dave. So in this case, I wanted to touch upon BGP link state first. So BGP link state has become kind of, it's not de facto, right? But it's kind of the preferred mechanism for a PCE to acquire topology from the network, okay? So this is BGP link state. It's a completely new address family with new NLRI types and new path attributes associated to each route that can be advertised from the network all the way up to the PCE, and we will be sending from a PCE, we will be acquiring all of the topology, all of the traffic engineering topology information that a PCE needs in order to be able to perform its path computations, okay? And this is key in networks that may have multiple domains, multiple levels, or multiple areas, depending on what you have. And if you will want to have, or if you will want to do traffic engineering across a network like that, okay? So, and then path computation element, right? So this is a protocol that is used to report LSP status, not only to report, but also to ask a PCE to compute a path on behalf of a PCC. You know, we have PCEs and PCCs. So PCC is a path computation client. PCE is a path computation element. They establish a session, and there is a specific messaging designed for a PCC to ask for a path to report the status of the state of a path, and also to delegate control of those specific paths. And this works either with MPLS, classic RSVP-TE LSPs, it works with SRT LSPs, and it also works, of course, with SRv6 LSPs. So that's it for me. So I'll just pass the control to Dave. Thank you. Thank you.
As we mentioned, these are IETF standards for doing traffic engineering. There's a few non-IETF, and I'll be going through just one of these. I mean, RSVP on its own is very good protocol for solving these issues, but in some networks, the scale gets a little bit of an issue. So move on to other kinds of mechanisms to manage their networks. And plus, when you go on to multi-domain networks, it becomes an issue with managing things overall, splitting them up segment by segment ends up being problematic for doing traffic engineering. So one of these mechanisms I'm going to talk about here is closed loop automation. There's three major important things with closed loop automation. There's the initial telemetry gathering information from the network about what's going on, how it's being managed. Number two is reacting to those changes by rerouting paths or creating new paths, as talked about by Diego earlier. But the important thing here is doing this to make sure that no instabilities result. So you don't get any flip-flopping behavior with it. As traffic goes up in one place, you move things over, then it goes up here, moves it back. You need to avoid those kind of things. So the fair bit of effort, and you should pay attention to that in your network, that you're not introducing that. Like closed loop systems have been in industrial systems for a while. There's well-known things to do to make those work out properly. There's several types of telemetry that we can be gathering from the network. Utilization's one, or bandwidth information about what's on your links in your network, as well as what's on your individual LSPs in your network, your tunnels. So we can do this to reduce the probability of congestion related discards. There's also latency. So when 5G slicing requires low latency paths, and if you're in the presence of optical path switching in your network, you want to be monitoring that and reacting to that as it happens in real time. And finally, packet loss can be an issue in microwave networks with rain fade. So you want to be able to react around that to redirect traffic that's packet loss sensitive. So the use cases for this are global ISP can deploy a path computation engine to control the rerouting of traffic through the network in order to minimize congestion throughout the network while achieving the SLAs for the customer. So a path computation element, or what I usually call an engine, but I think the people here in Charlotte with the car culture here would not be happy with the use of the word engine here. So especially the guys that were driving outside my hotel window at in the middle of the night at high speed down the roads here. So it basically provides the capability of doing basic path computation for networks. So by taking requests from the nodes in your network, which are called PCCs, and computing a path in the standard way that a node would do it. But it provides additional functionality on top of that. And these are defined in the stateful extensions where you can actually keep track of things, take into account bandwidth that's used throughout the network by all of the LSPs, and be able to make a centralized decision about how to move them around, fit them into the network in a globally optimized way. So you treat this as basically a tool, just like any of these other tools that Diego talked about. It's just one of your tools in your toolbox for this. You may not need it in your network, but when you're getting to high congestion levels and interaction between a large number of nodes in your network, and as your network's growing, you're going to multiple domains, it may become something worthwhile to look into. So basically what it can give you is reduced operational complexity. Everything is, bring all the information you need to understand traffic engineering is brought into a single spot. You get a unified network view of your network. A lot of customers will stop at this point in time. They just want to see the visualization of their network and how it all fits together. May actually still control the LSPs on the router, but But this provides a unified view where you can look at all the interaction between your LSPs and your network, how the utilization is managed, and how latency is results from your choice of path selection in your network. But you can go on and do path computation, maybe selectively in your network, and then adapt in real time to some of the telemetry stuff in a closed loop automation way. And as a result of that, you can end up with a very efficient utilization of your network that you wouldn't be able to do with a node-controlled solution where it doesn't have full knowledge of everything in the network. So the PC architecture here is showing, as Diego pointed out, a segment routing use case where we only deploy down to the head-end node, and there's no signaling going back and forth. It provides all instructions in here through a segment list defined as a mixture of node SIDs in this case and adjacency SIDs in your network. Breaking that down further, as Diego talked about, BGP-LS is used to gather the routing information and it provides a single point of connection into the PCE, into the traffic engineering database in order to compute paths. And then the PCE will monitor the network, and this works whether it's single domain, multiple areas, works regardless of the mechanism that's being used. So here are some of the messages. I'm not going to go through them here, but these are only the basic ones and the objects that are within those messages. But the breakdown here is key for this is the stateless messages. So PCB request and reply are for the basic operation that PCE started with, and then the stateful messages are for when you're storing information and doing additional work. The PCE working group at the IETF is still ongoing. There's further enhancements being developed. I'm not going to go through the details of that, but take too long. It's not a talk on that anyways today, but I just wanted to introduce some of the messages that you'll commonly see. So the use cases, as mentioned, is basic path setup for traffic engineering, using the same kind of metrics that the node does. It uses the same algorithm, so there's no concern about the way things work there. But then you can get into some of the optimization use cases where you're optimizing your resources by measuring the latency and utilization in your network, and then you can work at controlling resource allocation between different systems that you may have, and making sure that some don't consume too much bandwidth in your network, and control that centrally in a way that you wouldn't be able to do distributing it on the routers in your network. And finally, like as things always change, you need to re-optimize constantly to make sure the network behaves correctly. So again, real-world example of this, using PCEP basically to control the paths of LSPs in order to maximize the network utilization or efficiency. So like, for example, during like, since it's Super Bowl, just after Super Bowl, spike of video streaming traffic may not be the actual streaming of the TV session into your home, but it could be sharing of videos back and forth between people. Those can cause spikes in your network, and you need to be able to adapt to those quickly to make sure that your customers are kept happy. So here's an example of this of two LSPs set up in a disjoint way, but you can even extend this and allow it to have different source and destination nodes. So if you're using multi-homing services in your network, something that the node wouldn't be able to do even with without doing complicated admin group configuration in your network to achieve it. So the summary, this is, PCEP is bringing an important part of into your traffic engineering toolset, not a mandatory thing, but something to keep in mind if you're starting to get into highly congested situations. So in order to achieve some of these things and to lead on into an overall solution, you need to talk about the the APIs that are used for traffic engineering. So all of these APIs that I'm going to be talking about are Yang-based. I assume you're all familiar with Yang. I won't go through this in detail, but I mean, SNMP has been around for a while, but a lot of the core ability to manage networks and provide automation support is around dynamic models through Yang, and the ability to adapt those into a network and manage those across multi-vendor in a standardized way. So it's not only used to the node, but it's also used northbound of your management system to provide integration into your OSS systems. So it can be done through RESTConf and REST northbound of your management system to provide that. So one of the models is the IETF tunnel model or LSP model. So the draft is listed there. It's soon going to be an RFC. Basically describes the tunnels in a vendor abstract way. Additional model, several RFCs here describe the network topology. This is done as a set of nodes, links, and termination points that basically provide a graph of your network in a machine and human readable format. It's also done in a layered way so that you can throw several layers of your network as you build it up. So I haven't gone down to the lowest layers, started at layer 2 here. Layer 2 is the Ethernet layer shown by the RFC there. Layer 3 is obviously the IGP layer. And there's different information made available within that RFC for information specific to IGP. And then layer 4 shows the service view, which is basically shows the attachment points from your network to customers. So just the outside of your network as so if that can be provided to an external OSS system that manages just those service attachment points so that they can be managed independently. Here's an example of the machine or human readable format for one of these, which here's an LSP or a tunnel that's configured in a bidirectional way, shown in JSON format here, and shows you the simple configuration that would be used to configure one of these LSPs. And finally, getting into a little bit more on the BGP link state, which is mostly being covered already. This basically allows the aggregation of routing information from multiple IGP domains. So there's a new address family for this. There's performance metric extensions to it in order to get latency information carried within BGP-LS. And you can even traffic engineer across a network divided by eBGP links. If you're merging two operators are merging together, they can achieve end-to-end traffic engineering without having to change their network topology and move away from those eBGP links in the middle. And this allows basically the PCE to just get one connection in there. I know people don't want to add too much to BGP. It's always a tough thing to do, but I think we're down a slippery slope where this is happening a little too much. Don't blame me. I'm just the messenger. Yeah, there's a lot going into BGP these days, as you all know. And finally, pass it off to Mauricio Rojas, who I work with in the automation group, and he'll cover off some of the telemetry stuff and talk about the future talk tomorrow afternoon.
Thank you, Dave. My name is Mao, and I'm working also in Nokia in the network automation team, like you said. I'm going to work about telemetry. I know them is getting a little worn out, the topic here but I'm going to just talk a little about introducing telemetry for some people that maybe don't know. And I'm going to talk about a gRPC, and then I'm going to talk about why this is important, for example, for the closed loop automation with the PCE. Okay, here we go. Well, telemetry, well, I think the slide is very self-explanatory. It's about how can I be proactive? If you have telemetry, you have data, you can try to identify any issue in advance, like seeing a really weird pattern maybe on your traffic, or seeing that maybe some traffic is increasing in some of the interfaces, and you can take actions before to impact the user experience. Then you have performance optimization too. You can analyze the history of the information of your telemetry, and based on that information, you can take decisions on how you can optimize some of the routers interfaces. You see some of the routers are utilized, then you can try to put it, in some way that they can take more advantage of as part of the resource utilization. You have also capacity planning. You can take decisions how you want to grow the network, or maybe you don't need to grow the network. You need to try to make the network more efficient. Telemetry is going to give you that information. And also security. You see some sort of weird spike on the network, maybe you're under attack, and then you need to start taking some of the precautions to avoid that in that moment or in the future. Some of the components of the telemetry, and I figured this topology or this diagram on my own. Please don't blame me if you don't like it. But I'm seeing that lately many of the engineers are using JSON for the logs. They're trying to put some structure on the logs to make it easy for collectors to process that information and leave it available for any other follow-up applications, like, for example, InfluxDB or Prometheus or even Kafka. And then you also have the metrics. You have collectors like a GNMIC that can pull information directly from the devices through the gRPC. And then you can put that information in Prometheus and have other applications using the information. Kafka, for example, is a very resourceful tool if you want to share that information with other systems, to subscribe other systems and not maybe overwhelm Prometheus in that. And probably you're going to be using InfluxDB more for processing events and try to get that information inside of the events using that. Then you have Grafana, that is very popular, very open source tool. Is a very popular open source tool to display the information of your telemetry. And you can see patterns, you can see whatever you can get from Prometheus. You can connect Grafana directly to Prometheus. You don't need anything in the middle. And I'm seeing, I tried to submit a topic about OpenAI using that kind of stuff, but I'm still waiting for the approval. You know that right now AI is a little complex topic for many organizations. But you can have also OpenAI or create your OpenAI assistant to start processing that information and give you some insights that probably you are not seeing with your eyes directly in Grafana. You have also, you have the protocols, the legacy protocols like SNMP that are still being used a lot, but you have also gRPC. And everybody's starting to move SNMP to gRPC because of the performance. Because also it's working more natively with the YAML, then it's much easier for you to process that information, or for other applications to process that information if you don't want to have someone in the middle. And also because it's using proto buffers, it's very efficient in the network, and it's taking very, very low resources from going from the devices to the collector. And you have also microservices. Many of the collectors are working right now in Kubernetes on cloud-native solutions. And you can put it also in a public cloud in a Kubernetes cluster. And to talk a little more about GNMI, that is part of the gRPC protocols. GNMI is the protocol used for telemetry subscription. You can, it's using proto buffers. Proto buffers is also a really nice innovation because you're not tied to a specific programming code. You can have your client in Go and you have your server in Python. You're not limited in that case because you can see proto buffers library for almost every language you have right now on the market. And it's very optimized to try to use as less resources you can from the network to pull the data. And I think this slide, I showed this slide before. If you go to GNMI, you have many more capabilities than just to subscribe for telemetry. If you are not aware of that, for example, collectors like a GNMI-C also can be a customer or client, client solution to start pushing configurations directly on the devices. And you can use set for that. And also supporting Golang Go templates that make the things much easier. Then if you are tired of Ansible, you can start entertaining, for example, GNMI-C with Go templates. I would like you, if you can see that, because it's much easier than it try to work or deal with the different roles that you can have in Ansible, or sometimes you're not getting the speed that you're waiting for any configuration. You have also you can get any information of the state of the network, not just the stats or the telemetry information. You can get what is the actual configuration that I have for the state of the configuration of my device using set. Then there are many things that you can, use cases that you can have for GNMI. It's not just for telemetry. Based on the components of that, you have many things like you can use certificates. Then if you are a little worried because of the security, you don't want anyone to just go and start pulling telemetry or configuration information from your devices, you can use certificates. You can define those certificates in the collector and also in the devices. And you can also encrypt all the information that is going from the devices to your collector. And if you are also, well, this solution is also working with YANG, then make the things much easier. Most of the devices today support YANG, then it's not a big deal. Then basically, when you are doing a subscription, you can just go from the collector like a GNMI-C and start subscribing every device or any new device in the network and the devices are going to start pushing information. You can select what counters you want. You don't need to get all the data, only the telemetry information that you need. And it's not going to overwhelm the network for that. And also that collector can be later put in, GNMI-C, for example, can put the information directly in Prometheus. And then you can use Prometheus for every other application to start pulling the data, like a Grafana. You can have the software-defined network device or controller, like, for example, a module of a PCE controller that we're going to talk in the next slide. And you have also any network management system to start getting information from that to understand what is the state of the network. And then why I need a gRPC? Well, most of the new PCE controllers are using gRPC to pull telemetry information like the delay or bandwidth of LSPs. And based on that information, they can start computing different paths for the LSPs in the network and take real advantage of the resources of the network. Then everything that actually Dave was telling about the BGP-LS, how you can put the topology and start using PCEP to start computing different paths for LSPs. You can use also telemetry to start getting that information and create a closed loop automation solution directly for your transport. We are going to talk more about that. It's going to be a more advanced session tomorrow afternoon, I think at 5 p.m. And we are going to show a use case using Python and OpenAIs, how you can have something like that. For example, you have your PC controller, but you don't have the support of telemetry. You can use telemetry in order to start computing paths. Then using open APIs in Python, you can actually create your own solution or closed loop solution. You don't need to depend on the PCA controller. Then we are going to talk about that tomorrow. It's going to be a little more advanced. We're going to show also a little piece of the code of the application. We had a repo also over there. You don't use it, please, on production. It's just for the education purposes. If you want to use it, okay, you can fork that project and take the risk on your own. But I'm saying tomorrow we're going to show something more advanced on this use case. Okay. Well, we're almost done. Just additional resources if you want to just get information about all the topics that we were talking. We were using some of the information from the Packet Pushers blog for the PCE. And there are many other presentation talks that were done in Nanoc that you can go about GNMIC and on Container Lab, because tomorrow I want to use Container Lab for to show how you can manipulate a transport network. And I think we're done.